Hello, it's going to talk about in this class, okay, in this video, to design and study a regulated variable power supply, how to design and how to study this regulated variable power supply. It is one of the good experiment of MSc first semester. Here what we need is, we need a, mm, here we need a transformer, okay? Here we need a transformer. I want to show a picture of transformer over here. This is a picture of transformer. I hope you can see this, but my screen is being shared or not. Okay, let me show once again about this transformer. This is one example of transformer which we can see in any kind of electronic device. We can see such type of transformer. Okay, we need one transformer, and we connect. The shape of transformer will be like this, which we have already read in class 10. There will be primary binding and secondary binding of a coil. We need here step down transformer. We connect, here is a two terminal to be connected. We'll connect to directly to the power source of 220 volt, which we have in our regular houses. Okay, we'll connect to 220 volt of our terminal of our house or in the laboratory, wherever we like. And from here we have a 3 terminal as output. We need such type of transformer which have a voltage, output voltage as a 12, 0 and 12. Okay, we need such type of voltage. This middle one is called a center tap. Okay, center tap tap. Okay, center tap. It is called a center tap transformer of 12 volt, 0 volt and 12 volt. Okay, now what we do from here is we'll connect this and we'll have this 3 point from here. So this 12 volt and 0, from here we connect 2 wire, and we'll connect this 12 volt over here and 0 volt up to here, and this point will be grounded. And there are 4 diodes connected in such a way as shown in the figure. There is this line of a diode. Okay, these 4 diodes should be connected in such a way. We can connect this diagram easily with the help of diode. In diode, we can see there in the tip of in the end of that diode there is one mark. Okay, with that mark we can understand in which direction we need to keep a diode. Okay, this is the regular connection. I didn't show here anything. Here is a transformer. From the transformer output we need this 12 and 0 volt. But I want to say we need to be very much careful because we are working with the AC current, alternating current, because if we do little bit mistake, then we may get electric shock, because we just take a transformer, we connect directly, and we have a 12 volt output. We need to, one thing I want to tell here, we need to be sure whether we are getting this 12 volt and 0 volt or not. Here we can check this with the help of multimeter by adjusting it to the AC point, and after that we can supply it to this diode. And here this diode is organized in such a way that it allows only one part of the current to pass through it. Suppose it can allow only one terminal, one positive cycle or negative cycle of a AC to pass through it. So the main use of such type of diode is to convert AC to DC current. DC, whatever we get here will be DC, but some values of AC will be also out from here. We cannot totally convert all AC into DC. Here we deal with such type of thing. Okay, so from here, from this terminal, if we measure a DC voltage, let's see. Okay, we supply AC from here, and from here we measure DC voltage with the help of multimeter. Why DC? Because this diode play a vital role to convert AC into DC over here only. From here we'll convert, check once once the value of DC with the help of multimeter, and we'll connect this same point in the oscilloscope. In oscilloscope we can see this type of ripple. Okay, we will see such type of ripple, because what does this ripple shows that some amount of AC is again seen in this terminal VA. That is the main role of the ripple. Okay, it should not be like a total like a sine wave. Complete AC will not be there, but some part of AC can be seen as a ripple. But this is a very less value of ripple, less voltage of ripple. This voltage will be calculated. Ripple voltage should be calculated. Okay, with the help of oscilloscope, and from a same point we need to calculate um, DC voltage with the help of multimeter. So from here, we'll connect this capacitor of 1000 microfarad to the ground. Okay, we need this capacitor. And from here, we connect R4. A name of capacitor is R4. We'll check here both AC and DC at first. And this is R4 of 1 kilo ohm. And over here, we connect one NPN transistor of code BC547C. And from here, this is a base, this is emitter, and this is collector. This emitter and this is collector. And from here, we'll connect it to the base. And this base and the collector of another transistor will be connected in such a way in a breadboard so that it is connected with each other. And this from same point we'll connect to the collector, and from here we'll break it and connect to the base with R4 with this R4 resistor of 1 kilo ohm. And from here we'll connect the emitter to the ground, and from here we'll connect base to another Zener diode. Okay, here is a Zener diode. We'll connect it to the Zener diode, and from here we'll connect one R3 resistance of value 2.2 kilo ohm, and from here we'll connect it to another R2 whose value should be greater than 1 kilo ohm, because if its value is less, then all the current will flow over here and this transistor may get damaged. So in order to protect this transistor, we'll keep here very much high resistance so that all the current will not be ground with this terminal. So this transistor will be kept safe if we keep R2 value more than 1 kilo ohm. And this R1 value, we'll set it. Later on, I'll talk about this R1, how to keep this R1. And from here, we'll keep a load resistance of greater than or equal to 1 kilo ohm. Here, load resistance also will be greater than or equal to 1 kilo ohm. From here, we'll measure output voltage. From here, we measure input voltage. Okay. Now, sorry for this disturbance. From here we measure output voltage, from here we measure input voltage. Now what thing is to be measured? From input voltage we measure a DC input with the help of multimeter, and some ripple can be seen. This ripple must be measured with the help of oscilloscope, and from here same thing we'll measure from output terminal. That is, DC voltage should be taken out with the help of multimeter, and we need to see whether there is some ripple still or not. There will be minimum amount of ripple so that we cannot convert directly all the DC into AC. Some part of AC, small properties of AC can be seen in such type of terminal. If we go through millivolt here, then some little amount of millivolt in 0.006 or 0.004, in that value we can see, suppose 0.004 millivolt of AC can be seen over here. Okay, and some amount of DC, more amount of DC can be seen. So what makes it makes one thing clear, that this DC is converted here to AC. Oh, sorry, AC is converted here to DC, but little bit more amount of AC current can be seen with the help of oscilloscope. But whatever we measure from here, the value of this, what do we call, AC will be less. We can see this easily in our oscilloscope. Whenever we connect it, we'll go through millivolt, then only we can see the fluctuation over a ripple. We can see ripple over here, but here we can see ripple in volt terminal. We can see ripple here in millivolt terminal. So from here we connect RL. Our circuit diagram is over. Okay. Uh, I have talked about this thing, and be sure that this R2 and RL value will be more because it is directly connected to the ground. So its values will be more. Otherwise, this transistor will be damaged. Okay. It is an experiment to be known. Now, it is a data to be filled. Okay. We'll keep a capacitor of 1000 and we'll keep the R1 value, three different R1 value. Let's talk about the R1 value, 1 kilo ohm. We'll keep R1 1 kilo ohm. And what we will see, we'll not keep any load. There will be no any load. We'll remove this load. And what we'll check? We'll check input voltage from here. Okay. We'll check input voltage and input ripple voltage. Ripple voltage at point A and at point B naught. Suppose this point is A. I have kept here BA because I have shown here BA because this point is A. Forgot to mention over here, this point is A. Okay, from this point A, we'll take out the ripple voltage. Ripple voltage can be taken out with the help of oscilloscope. And DC voltage at the same point. Now, without any load, we have measured here ripple voltage and DC voltage. And without any load, we need to measure here ripple voltage and DC voltage again. Okay, and such type of value will be plotted over here. Now, another, we need to keep the value of RL greater than 200 ohm, but we'll keep here greater than 1 kilo ohm. Okay, 1 kilo ohm. Now we'll keep here 1 kilo ohm. 1 kilo ohm value. And we'll check the ripple voltage again in point A, again in point A, two type of voltage, DC voltage and ripple voltage. If we keep here the load resistance of 1 kilo ohm, because I already told that this resistance will be more than 1 kilo ohm, whatever it is mentioned on that table, we need to keep it more than 1 kilo ohm. Sometime in our practical, if we keep here 1 kilo ohm, the resistor is heated too quickly that if we touch that resistor also, we may get our hand burned because we are supplying 12 volt AC current from here, and this is being converted into something, some amount of DC over here. So the DC voltage is also too high. So because of that, this resistor will be heated too quickly. But I recommend to do this experiment very quickly if we connect here 1 kilo ohm resistance. But don't try to connect less than 1 kilo ohm. Okay. For a short interval of time, we can connect 1 kilo ohm and we can measure DC voltage from here, ripple voltage from here, again DC voltage from here, ripple voltage from here. Again, we need to take out this and we need to keep here 2 kilo ohm because 1 kilo ohm data of ripple voltage, DC voltage at point A and ripple voltage and DC voltage at point B can be taken out over here. Again, if we keep here 2.2 kilo ohm resistance, okay, 2.2 kilo ohm resistor, and we can do a same thing from point A and point B. Okay, point A and point B, we can do same thing from here, point A and point B. BA and BB can be done same thing. And another is we can keep here 3.3 kilo ohm resistance. 3.3 kilo ohm resistance in a load terminal, and then we can measure here DC voltage at point A and ripple voltage at point A, DC voltage at point B naught, ripple voltage at point B naught, and then we can do this experiment. And same thing should be performed for the R1 value 2.2. We need to change this R1 value to 2.2 kilo ohm, and we need to perform again without any load. We need to check here DC voltage, ripple voltage. Here we can check DC voltage and ripple voltage at the B naught. Same thing we need to do for no load, and again for 1 kilo ohm, 2.2 kilo ohm and 3.3 kilo ohm, we can do same type of thing. And for 3.3, again we can check for no load, and we can check for 1 kilo ohm, 2.2 kilo ohm and 3.3 kilo ohm. For each and everything, we need to trace a curve for this ripple voltage. In one curve, we can trace one data. Suppose in one curve, we can trace for capacitor 1000, resistor 1 kilo ohm, and no load. This one and this one as an input and output, or at point A and at point B naught. Let's call it as a at point A and at point B naught. We need to trace a curve up and down. You can trace one curve, two curve, three curve, four curve, and 5, 6, 7, 8, 9, 10, 11, 12. 12 curve we need to trace, and there is formula for BR. Okay, in our book, I haven't copied here. In our book, there is a formula for BR. Later on, I can connect this formula over here. Okay, this PR should be calculated. And the one thing is that we need to trace a curve. Okay, according to the teacher, we found that we need to trace a curve for this data. Okay, for this, how to trace a curve, I would like to go through my copy for a while. Okay, see some. This RL is fixed for 1 kilo ohm. See here, for value of R11, okay, for this fixed value, we need to trace a curve for DC output voltage and RL. Okay, RL, what is the value of RL? 1 kilo ohm, and DC output voltage for 2 kilo ohm, DC output voltage for 3 kilo ohm, and here DC output voltage for 0 kilo ohm. Okay, we need to trace a curve between this DC output voltage and this resistance. We need to keep resistance in x-axis. Suppose 0, 1, 2.2, 3.3, and we'll see the voltage whether it is increasing or decreasing for this 1 kilo ohm. Similarly, for 2.2 kilo ohm without any load, this one, this one, this one, this one, we need to trace another curve for this. Okay, we will not we consider this in our mind, and we'll keep this resistance towards x-axis and this DC voltage towards a y-axis, and we trace a curve. And for 3.3 also same thing, we can trace a curve. So we have a 3 curve over here, sorry, 3 graph over here. Okay, whatever we trace, that will get as a in a graph paper. And another is, next time we need to keep RL fixed. RL will be fixed. That is for 1 kilo ohm. We'll keep fixed for a less 1 kilo. We'll not keep fixed for all 1, 2, and 3. Okay, I'll make my words clear. For RL, we will, what we will do is, for this RL, we'll take only 1 kilo ohm. Here 1 kilo ohm, here also will be 1 kilo ohm, and here also will be 1 kilo ohm. We'll trace the curve between R1 and B output, again keeping this constant for 1 kilo ohm only. We'll take only for 1 kilo ohm. If you go for 2.2 kilo ohm, we have another curve. If you go for 3 kilo ohm, we will have another curve. For this 1 kilo ohm, suppose for this one curve 1 kilo ohm, 1 kilo ohm is here 1, 2, and 3 place. So what we will do is we'll keep this resistor because it is not fixed now. Because before we have made this constant, we'll trace a curve between this and this. Now we have made this constant for a while in our imagination. We have traced this constant. So for this one value will be here. Another 2.2 value will be here. Another 3.3 values will be here. Now I'm talking about this value. R1 will be in x-axis, and this output voltage will be in y-axis. How this curve increase? It is not clear that it will be increased by this way or that way. We need to trace a curve, and then we get our graph by this way. Okay, up to this much, if we do it, and if we have some kind of error, then the error calculation also should be done. I hope that I made more or less clear. Mm, I have written here R1 value will be changed from 1 to 2.2 up to 3.3 kilo ohm. It will be changed this value. I have already talked because this one makes our work very much clear. Okay, I hope this video will be informative and little bit it may be useful to do some experiment in a laboratory. So I would like to uh, say thank you. And before leaving my class, it is a voltage regulator, and the main work of voltage regulator is whatever be the value of resistance, the output voltage should be consistent. That is, it should be same. So for that, we will take out the BR percentage. And it is said that the value of BR percentage, if it is very much less, then our voltage regulator is very much stable and reliable. Whatever the changes is made here in the resistance, output voltage will be same. We have read about this thing in our class also. So it is the main work of voltage regulator. It gives a constant output. So let's see whether the output will be constant or not with the help of this calculation BR percentage. If there is some type of error, then we need to calculate error also. Because it is experiment, there may be some kind of error, there will be some kind of error. So let's do our experiment very much carefully, and let's be sure whether the 12-volt input is being supplied or not through the transformer. And be safe and do experiment, okay, and enjoy doing experiment very much clearly. And if you feel this video will be informative to you to do such type of experiment in lab, then please reply me over here. Okay. Okay. Thank you very much. Thank you.